Hello everyone, welcome to the International Conference on Digital Technology Driven Engineering 2025. Today I will be presenting our research paper titled Synergistic Wear Corrosion Interaction in Aluminum Silicon Alumina Composite Microstructural Electrochemical and Tribological Assessments. This research was conducted and authored by Farah, Ammar, Ibrahim, Zeyad, Kadhim and Mohammed Abdulrazzaq from the from the Material Engineering Department at Al₂O₃ University, located in Baghdad, Iraq. In this presentation, we will explore how reinforcing aluminum alloy affects the performance in harsh marine environments. In this slide, let's begin to define the core problem and our motivation. We are focusing on phenomena known as tribal corrosion. This is not just simple wear or simple corrosion, it's something fused and synergistic material, fluid resulting from the interaction of wear and corrosion acting together. This is critical issue specifically in marine environment where components face both friction and corrosive seawater. The challenge we face is with aluminum silicon alloy. While these alloys are high valued in this industry for being lightweight, they unfortunately suffer from low surface hardness, which limits their durability in these aggressive conditions. To address this limitation, our proposed solution involves reinforcing the aluminum silicon matrix with 3.5% weight alumina ceramic particles. We believe this addition will significantly enhance the surface properties and resistance of the alloy. Our research objectives are fourfold. First, fabricate these aluminum silicon matrix composites using the stir casting method. Second, to analyze the microstructural distribution of the particles. Third, to evaluate the corrosion resistance in a 3.5% sodium chloride solution. And finally, to determine the synergistic material loss or the tribal corrosion behavior. In slide 4, materials and methods. Moving on to our methodology, we use stir casting at temperature between 715 and 718 degrees Celsius for fabrication. For testing, we conducted dry sliding wear test using spin-on-bed setup according to ASTM G99 standard. Electrochemical behavior was analyzed via potentiodynamic polarization and the full corrosion behavior was evaluated using an integrated sliding corrosion test per ASTM G119. In this slide, moving on to our findings, let's first look at the microstructural results. As illustrated in Figure 1, the FEM micrographs clearly show a uniform distribution of aluminum reinforcement particles within aluminum silicon matrix. This formally is crucial for consistent material performance. Furthermore, the image reveals that we achieve strong metallurgical bonding between the ceramic particles and the metal matrix. Unfortunately, we observe no significant agglomeration or clustering of particles, which indicates the effectiveness of the stir casting process we employed. If you look at Figure 2, which shows the wall surface, you can observe specific wear mechanisms such as abrasive growth and microdelineation, alongside thickening corrosion shown in image C. This visual evidence helps us to understand the physical degradation of the material. In Slide 6, wear behavior results. Regarding wear behavior, the hardness increased with the addition of reinforcement. As you can see in the data, the hard ceramic particles resist plastic deformation comparing the unreinforced alloy to the composite. The wear rate was reduced significantly. For example, adding 15% aluminum reduced wear by 58% compared to the unreinforced alloy. The specific wear rate dropped from 4.85 to 1.98 times 10 to the power of -4. In Slide 7, corrosion performance. In terms of corrosion performance shown in the Figure 3, the corrosion performance curve shifted to more noble positive volume with the reinforcement. Gradually, the current density curve decreasing significantly from 13 down to 6.3 microamps per square centimeter, indicated improved polarization resistance. In this slide, let's analyze the corrosion performance, which is a key part of this study. Looking at the potentiodynamic polarization curve in Figure 3, we observe significant improvement. The corrosion potential curve shift towards more noble positive volume for the reinforced composite compared to the unreinforced alloy. More quantitatively, the current density or the core decreased dramatically. It dropped from 13 down to 6.3 microampere per square centimeter. This reduction is direct indicator of slower corrosion rate. This data confirms in slide 8, Tribological and Synergistic effects. Now discussing the core of this study. Tribological. We calculate the synergy factor S for unreinforced aluminum silicon alloy S was greater than 1.5, indicate high degradation. However, for the composite S dropped to the approximately 1.1. This proves that the reinforcement effectively mitigates the accelerating effect that wear usually has on corrosion. In slide 9, surface morphology analyzed. Figure 5 illustrates the surface morphology under wear only. We see abrasive growth under corrosion only. We see chloride indicate pitting, however, under tribal corrosion. We observe a computation of smooth wear tracks and accelerate pitting, confirming the intersection between the two mechanisms. In slide 10, conclusion. To conclude our presentation, stir casting successfully produced homogeneous composites. The reinforcement improved both wear and corrosion resistance significantly, while synergistic effect exists is significantly dampened by the presence of the ceramic reinforcement. Therefore, the composite is highly suitable for marine application involving friction. Thank you for your attention.